I'm Chris Phelps. I'm from Boulder, Colorado. Work for a company called Tendril. We do energy analytics and energy intelligence. And as we do that, we want to try to have reactive systems kind of following the model laid out in the reactive manifesto. We want systems that are scalable and responsive and do all those sorts of things. So we want systems that respond in the kind of timeframes that we need for batch traffic or for user traffic. We want resiliency so the systems can deal with failure and recover from failure. We want to be elastic in order to support those and be able to scale things up and back down so we save money when we don't need it. We can avoid things like batch processes causing outages on our live website and things like that. And then there's some kind of message-driven stuff that supports all of that. So if you're trying to develop that kind of system, you want to start looking at asynchronous things and how to manage being asynchronous. How do I take some work, start working on it, and keep from occupying the rest of my resources while I'm waiting for things to happen? If I'm building a multi-service thing and I have to go talk to a separate service or talk to some third party to get data, if I have to go off to the database to get some data, how can I use those resources effectively while I'm waiting for responses to come back from those other services? This is the end of 3 days at Scale by the Bay. You've probably seen a bunch of talks that have talked about asynchronous behaviors and asynchronous effects and how to manage effects in your system. And we'll talk about futures, which are a good mechanism for us to do that asynchronous effect handling. So kind of a really brief history of what's going on with these future things, right? So way back in the day, probably 2006 or 2007, we started to develop in Java this future representation that let us represent a value that has not completed yet. But at the time, we really couldn't do anything with that. We could say, is it done yet? Or let me block and wait for it. And that's not a whole lot better than just blocking and waiting for the thing in the first place. Twitter and Akka came along and they started building more sophisticated ways for us to manage that without having to just sit and block on the thing. Start giving us callbacks when the work is done and that sort of thing. And then in 2012 with SIP 14, we moved that into Scala Standard Library and built the first Scala Future Library. So we've still got Twitter stuff from that time frame, and the Akka stuff when we had 2.14 all kind of deprecated and moved into Standard Scala Library stuff. So Scala Standard Future we've had around since 2.10. It's continued to have things happen with it. And actually, I don't have on this slide, but in Java 8, we started to get Java completable futures that built more of this stuff back into the core of Java. So in this talk, I'll kind of go through Scala futures, how to use them, Twitter futures, how they differ to Scala futures. I'll mention really briefly Guava. You can say boo now or then. Talk about completable future. We'll touch on task for a little bit, and then we'll give you some kind of comparison summaries. So let's start with Scala standard future. So what makes up a future in Scala? Basically, we've got 3 states that a future can be in. It can be unresolved, resolved successfully and it has a value, or resolved with failure and it has some sort of throwable associated to it. We have an ability to make immediately resolved futures for purpose of chaining together pipelines. Futures which are immediately resolved successfully, futures that are immediately failed. Then we have promises. I'll talk more about promise on the subsequent slides. Promise is a way for us to grab the starting point of that computation, pass someone else the future back from that, and then later resolve the promise to resolve their future. And then there's a bunch of combinators for putting these things together and working with them. So how do you get a future? Well, the trivial answer is you call somebody else's library and it returns a future. But that's not very interesting because it just raises the subsequent question, how did they make the future? In the regular Scala library, we have apply on the future object, which will create a future body and put that into an execution context. Or as I just started to allude, we can make a promise. So let's start with apply. We have to have an execution context that these will run in. I'll talk a little more about that on a subsequent slide. In this case, we're just going to grab the global one. Then we use future and pass it a body, and this calculate slowly is going to happen inside the execution context. That's going to yield this future event that I can pass around and do something else with. Creating one with promise, on the other hand, I will make a new promise. I will return my client the future end of that promise, so that's how my client can wait on my result. I can go off and do my calculate slowly, and when calculate slowly is done, I fill in the promise with the successful value, and the client receives that as completion on his future. So the client can set up his callbacks and do all that kinds of thing, and he gets those callbacks called when I resolve the promise end. So the way this works, we've got a producer and a consumer. Producer's going to build the new promise, return that future to the consumer. Consumer's going to register callbacks on that. At some point, the producer completes the promise, and the callbacks are executed on the consumer. So callbacks. So in this example here, I've called the calculate method, and calculates return me a future. I'm going to use onComplete to give a partial function. That partial function, when it receives a success, can do something with the result. When it receives a failure, can do something with the throwable that's inside that failure. So that's a single partial function that's given to onComplete that handles both sides of those. But what if I want to build subparts of that? I just want to handle the success case. I just want to handle the failure case. So in 2.11, we have actually an onComplete. So this slide's not completely up to date. Have an onComplete, which takes a partial function and just operates on the success. This is only called in the case when the future resolves successfully. And an onFailure that's called when the future fails, and is a partial function that looks at the exception. So in this case, I haven't done anything particularly interesting with res or with t, but that's a full partial function. We can do as much as we want. Maybe in our t case, we'll look at different kinds of failure and respond differently in those cases. Maybe res is something non-trivial, and we're doing some kind of matching or some kind of more to do work in there. In 2.12, both the onComplete and the onFailure are deprecated. They're still available, but the preference in this case is to use for each. I guess the one thing I don't display here is what's the signatures of these, right? So the onComplete and the onFailure were both partial functions yielding unit. And in this case, we make that kind of more explicit with for each and say this is a thing that is called and does side effects. It's not returning a value, it's a unit. And then we have this failed combinator, which lets us take the failed one, turn it from a future of A to a future of throwable. And that subsequent future is then resolved successfully with the failure from the first future, and that's why it's failed.forEach. But rather than doing those things that are just side effecty callbacks when the future succeeds or fails, instead we prefer to build chains on top of these and chain futures together so that they can do other things. And the main mechanism we have to do that is map, or maybe the first mechanism we have to do that is map and flat map. We see these on many, many types in the Scala standard library, and they all have basically the same signature. So Map is parameterized in S. This is on a future, which is itself parameterized in T. So then we have a function that takes a T and returns an S. You pass that function to map. When the when the future resolves, when it resolves successfully, this function is called, pass the value within that future. It returns the S. But I've built a pipeline here, right? So what comes back from that is a future of S. So you pass me this function now, and I say, I'll give you now a future value of what your function returns to me. Flat map lets us take that up one more step and says, the method that you're going to give me itself produces a future. So the map case, this is something that's going to happen right now. The flat map case, this is something that is going to yield another future. And I want to chain those two futures together. So when I get a callback from the first service, I make a call off to the second service. And those two future contexts are chained together, and now I or client can set up callbacks onto that. So let's look at an example of that. So I have a calculate method that makes this first future. I have a simple method that takes an int and returns an int called scale. And I'm going to hook that up as a callback on the initial future using map. So when my future resolves, the value that's in that future is going to be passed to scale. Scale is going to calculate it. And that's the future int that I get out of all of this. So scaled itself is a future. Recalculate is one that instead adds another layer of future. So we flat map this. When the first one succeeds, we'll call the second one. Recalculate will create a new future. We'll chain that together. Recalculated is now a future that I can set up callbacks on or do something else with from there. And once we have map or flat map, then we have some standard Scala syntactic sugar called for comprehensions. And these let us chain these kinds of classes that have maps and flat maps together into something that looks more iterative, right? So we could have done this with a bunch of nested flat maps. Instead, we'll use the for comprehension to chain these all together. So I calculate, I have a future, I recalculate, I have another future, and then I can scale the final result. And this turns into, underneath, a set of calls to flat map, map to yield these all together. So these are entirely equivalent to calling individual calls to map and flat map. And I don't have a slide that shows what that desugar is, but it's a very standard thing. You can look it up. So let's talk about some other combinators that you use to start putting these things together. So a couple that I've displayed here, fold left is a way for us to take a list of futures and combine their results together in some way. So whereas all of our previous examples were chaining one after another, this is, I've got several results, and I want to do something to combine all those results together into one result, where these are typically results of the same type. I make 3 different calls out to my user service, and then I want to combine them together to have one final user object or something like that. First completed of is a way for us to race several futures, and we'll get back the first one that finishes. So maybe I'm making a call to 3 different nodes, and I want to take the first one that comes back. And sequence, and I put sequence on this slide because it's the simpler signature, but the slightly more powerful version is called traverse. This lets us take a list of futures, actually a traversable of futures, so strictly more traversable things than just lists. But a traversable of futures and turn them into a future of traversable. So I have my maybe I go off to a user service and I make 3 different calls to the user service to get 3 different users, and I want to turn that in at the end to one big list of users. I've gone from a list of future users to a future of list of users by using sequence or traverse. So let's talk about execution model. So these things have to finally run somewhere, right? And the way this works for Scala standard future is with this execution context. I showed it at the beginning that we were grabbing the global one. We can also pass that explicitly and pick a different one. So what happens with this body is the body gets submitted as a runnable that's put onto that execution context. And it's up to the execution context to decide how do I allocate that to threads. Right? So the execution context may be thread pool oriented or something like that, and it's taking that callable and deciding where and when to run that callable. The key here is that every one of our bodies goes back to the execution context, and the execution context then potentially puts it on its own thread or does whatever. So in the case of the global execution context that I showed before that I was grabbing implicitly, that's a fork join pool is what the standard one is implemented as. And everything that we submit as a body in a map or a flat map becomes its own callable, gets its own thread. So, but we can also write our own executor or execution service to do different things, and that's some of the tricks that we play later on to look at some of these other execution models that other frameworks do. Why might you choose to use the implicit or use something else? Control over pool size. If you're doing a lot of long blocking operations, there are other pools that are better for that. If you are managing your own set of pools and maybe you have a general pool that you want to do a lot of things with, and then you've got a special pool that you use just to do, just to frobnicate the things, you can send just this result to the frobnicator pool. Let's talk about Twitter. So there's some differences between Twitter futures and Scala futures, and any of you who've messed with these, have run into those very quickly. So the combinators, the execution model, and cancellation are the things that we're going to talk about here. I was told just a couple days ago that locals are the best thing about Twitter futures, and I'd never heard of them before. The documentation for them isn't super great. So I'm not going to talk about them now, but there's another difference. It's your bonus. So Twitter futures have most of the same kind of combinators. We've still got filters, maps, flattens, for eaches, and with futures. With filters. I didn't talk about a lot of these in the Scala standard one, but many of these are there in the Scala standard one as well. Filter, right, lets us return or not return the result based on whether the predicate succeeds. Flat map we talked about before. Flatten is for when we have a future of something, to turn that into a single future by chaining the two futures together. For each we talked about before, that runs a side effecty method when the result's there. Map we talked about before, that runs a non-side effecty method when the thing is there. And with filter is actually part of the underlying mechanism for how the for comprehension guards work. But again, takes the result and applies a predicate operation to it. But kind of more interesting are what are the things that Twitter futures add that Scala standard futures didn't have. So a couple of these at the top are by and within. These take some sort of timer and some sort of time. So by lets us say resolve this by this time. Within takes a duration. Let us resolve this within some amount of time. So you'd typically use that for some sort of scheduling kind of thing. This is not really a timeout sort of thing. We have parallels and selects and wins and while do's. All of these are about using futures to control other futures. So parallel takes and runs the same operation n times in parallel. And you see it gives us back a sequence of futures. Select lets us take a sequence of futures and grab the first one that comes back and the list of the rest of them that are there. So it's like racing without discarding all the rest of the things that fail the race. When you see is eager, it's not taking a lazily evaluated predicate. So when this case is true, run this future. And while do is reevaluating. So this is while this predicate holds, keep evaluating the future. And that says future of unit, but that's surprising to me if that's really doing iteration. But the theme of these, right, the theme of these latter ones is observing and choreographing other futures, using futures to control the behavior of other futures and control whether we proceed with computations. Many of the standard combinators that we have in the Scala standard library are also there in Twitter, but have different names. So is completed versus is done. Value in standard library versus poll in the Twitter future. Recover in the standard library versus handle in Twitter. Recover with instead of rescue. Zip instead of join. Zip with instead of join with. But I lied to you a little bit. A bunch of these in the Scala standard library take the execution context, but in Twitter they don't. So what's up with that? So the Twitter execution model is different from the Scala execution model because it's based on executing eagerly in the thread that resolves. So we end up with this pipeline that tries to stay in the same thread. You can fork to another pool, but you're going to try to stay in the same pool. So when the first future resolves, the thread that future is running in runs the callback. And if you set up a callback and the future's already resolved, you'll execute that callback body immediately in your thread. So there's actually an interesting thing that I discovered when I was first putting this talk together, and I was really surprised about why the thing failed in a certain way. And it turns out that I was running synchronously to me because the future that I was setting up and trying to wait on was already resolved. Just the way that I was building my test case, I had a very quickly executing future. I immediately tried to add a thing to it, and instead of that happening off in the future in the thread of the work that I was trying to do, I did it right away in me, and I ended up with, in my thread, and I ended up with context from my thread, not context from the running thread. So future.apply runs the body immediately in my calling thread. So if I want to run in a new future, how do I do that? That's with an explicit future pool. So I've built here an unbounded pool. If I immediately just do future and calculate, this is going to run right away in me. And if this calculate's expensive, I'm potentially blocking myself, right? Versus if I do on the pools apply, then this executes, it gets submitted to that future pool, I get a future back, and then I can run along and do my thing. Another big reason that you might use Twitter futures is cancellation. But cancellation is not as permanent as maybe you'd think. So from the promise side, you can interrupt by using raise, that you pass a exception to the thing as you raise it. The future is not resolved, but it's marked as interrupted. And then inside the running calculation, you can check for interruption. I'm going to speed up just a little bit. There's also a raise within that can add a timeout and will automatically raise your future with an exception when the timeout expires. So let's look at that. I have an unbounded pool. I make a promise. Inside my inside my body. I'm going to do the expensive calculation, and then I'm going to check and see if I'm interrupted. And if I'm interrupted, then I'm going to finish the future. If not, then I'm going to perform the next calculation. So I need to check between expensive parts whether or not I'm interrupted and make a decision whether or not to continue. And then from the outside, somewhere where we've got the original promise, we can fail that with I give up. That causes the future to be interrupted and allows the body to check that. Bijection, if you need to operate in both Scala futures and Twitter futures, the bijection library lets you convert between one or the other. You pull in some imports. In this case, I've renamed them Scala future and Twitter future. I've pulled in the as method, which gets me some syntax, and the bijections themselves to get all the conversions. And then I can do response, which is a Twitter future, dot as Scala future to change it between. And what this is doing internally is setting up callbacks to make this happen. This is not just a typecast, but an actual wiring up of callbacks so that these two things work. I'm going to say very, very little about Guava. Guava was a great library in its time. It's really painful to use from Scala. In particular, listenable futures are very painful to use from Scala. They don't chain. The syntax is just not comfortable from Scala. If you have to do anything with them, you can use some third-party things to biject those together. So there's this thing called guilt foundation classes that provide a lot of these bijections to convert between the two. In our case at Tendril, we have a lot of legacy code that was built around Java and listenable futures. So we really do care a lot of times about converting back and forth between those. But if you don't need to do that, I would, at this point, avoid it as Scala developers. So let's talk about Java 8. So in Java 8, we got completable future. It was trying to take more of these sort of future ideas back to the Java ecosystem. That gives us very similar rough shape to what we have in Scala. We've got a future with callbacks. We've got some sort of pipeline-y sort of behavior with promises and futures. In the completable futures case, the same object is both the promise and the future. It's both ends of that pipe. We could create as a promise. We can use supply async or run async to create runnable bodies that get submitted to the executors. So an example of that, so I have a completable future. I'm going to apply async this scale transform. Then apply async is similar to map, but it's going to happen in another call to the executor instead of in the same thread. At the end, we have a handler. The handler here, this is a very Java-like sort of signature, even though I'm showing this from Scala. So we get past both the result and the throwable. And if this future completed successfully, we have a non-null result and a null throwable. And if this failed, we have a null result and a non-null failure. So we have to take this, we have to say if R is null, we do the happy thing. Otherwise, if T is null, then we do the exception thing. So we don't have two separate methods that are called in those two cases, we just have one method. And then this completable future behaves like a promise as well, so at some point later I can complete that. And then anybody who's got a handler registered will have it fired. So the execution model is sort of a mix between the Scala execution model and the the Twitter execution model. So we have two different methods to indicate whether we're sync, meaning that we execute the body immediately in our thread, or async, meaning we submit the body back to the execution context. So we've got pairs of many of the methods. Apply async. Handle async. Regular version, when the future completes, we're going to execute it immediately in our thread. The async version, when the future completes, we're going to submit it back to the execution context, and the execution context potentially is allocating a new thread to do that. Default executor we get is a common fork join pool based on the number of cores. And what that type of pool does is typically makes a new thread for everybody. There's some configuration there that prevents that from happening, but typically it's going to create a new thread. Comparing the combinators between the two, we have variants to deal with runnables and functions, suppliers and consumers. We don't have a recover with, so we can't take a failed future and replace it with a new future operation that's going to resolve it. We can just recover exceptionally and handle the problem and do something with the problem now. So I didn't really cover this, but in the Scala version we have recover with, and you say recover this failed future with another future that's meant to replace it. I'm not going to mention any of the rest of that. Let's talk about tasks. So for purposes of this, we're going to think about tasks as lazy futures, futures that don't immediately start to execute. So all these other ones that we just talked about, they're starting execution of their body potentially right when we create them, right? In the Twitter case, we immediately started to do that on the caller thread. In the Java case, we submitted it to the execution context, and the execution context is potentially creating the new thread as soon as immediately to go start doing that work. But in the task case, we're not going to start that computation running until we actually tell it to run. So we can explicitly run it with, actually, one second, a few of them that I'm talking about in general here, Scala, Z, and Monix, both have roughly similar shapes and roughly similar sorts of semantics. FS2 has its own implementation of tasks that it uses internally, and I believe they're migrating that to CATS effects in newest versions. John DeGoes gave a good talk a couple days ago about Scala 8.io, and then there's also work going on in the CATS community to make a slightly more general effect for asynchronous deferred computation. So Scala 8.io and CATS effect. So one of the upshots to not evaluating immediately is that we could potentially evaluate the same future multiple times. And the reason why that's beneficial for us in task is because we have the option of whether or not to memoize, meaning save the result the first time that it's available. So we can build a task, build this whole pipeline around the task, and we can choose to not memoize it and just run it now, and then run it again in a couple minutes, and then run it again in a couple minutes. So we've set up a pipeline that we've reused again and again, or we can choose to explicitly memoize it, say run it this time, store the result, essentially cache it for the rest of the life cycle of the objects. Execution contexts, execution models are typically trampoline, and I'll talk about that a tiny bit more. And there's some cancellation to various degrees in all these models. So I'm mostly going to focus on Monix here. So in Monix, we can create tasks using apply. We can run that task and give it a handler at that time, and that handler, just like we've seen before, is going to execute when the thing's available. If we want to explicitly run and memoize the result, we task.memoize. If we want to cancel, when we called our run async, we actually got a cancelable future back. And then we can cancel that. So let's talk about the execution model. Execution model for these is something called a trampoline. It's almost always controlled by some kind of scheduler. In the Monix case, the scheduler has a few different modes that it can operate in. The default one is batched execution. And what that's going to do is try to keep running on the same thread as long as possible, and then periodically forking to a new thread. So after you reach a number of tasks on that queue, fork to another thread to do more. There's always async, which does everything in its own thread, and there's synchronous, which tries to do everything on the same thread. And so what happens is, We submit these units of work to the scheduler. We're going to execute those on the same thread within the executor. Whenever we hit a failure case and we need to clean up, or we hit an async boundary, then the scheduler is going to fork to a new thread. But we can also explicitly fork as we go through that. So in our pipeline, we can say, I want this next piece to happen on its own thread and fork. Or we can use this async boundary thing to cause an opportunity to fork. I mentioned up at the top, async boundary is forced after a certain number of pieces of work. Async boundary lets us force that boundary at the place where we want to put it. And the purpose to that is we want to either fork to a new thread, or we want to offer the ability for the system to fork us to a new thread, or we want to offer the ability for the system to cancel our thread at that point. So this is very much like the interruption status that I showed before. This is sort of being cooperative and saying, here's a point in my workload that I could pause. We can also use async boundary to switch to different schedulers. So in this example, I've got a task which is always forked to a new scheduler, to the I/O scheduler. I have my initial task in source. I'm going to flat map to switch to the I/O scheduler. I'm going to async boundary to switch back to global, and then I'm going to set up an on finish, and I'm going to run this whole pipeline. So let's look at a comparison of at least the future parts that we talked about. We've got Scala, Twitter, Guava, and Java. Promise-like creation in Scala and Twitter comes from promise. In Java, it's all completable future. We can create async via apply in Scala on the future companion object, in Twitter on a pool. And Java, we can supply async to submit a callable to the execution context. Execution model. Scala runs in an execution context, so everything gets submitted and potentially gets a new thread. Twitter, the completing thread runs the body. Java, the completing thread, or the executor runs it depending on the method that we used when we built the pipeline. Supporting for comprehension. Scala and Twitter are both based on map and flat map, so that you can use for comprehensions to build these pipelines. Java does not, so you have to use the other mechanisms, but you can play games with conversions and extension methods to add map and flat map that call to the right Java methods. Scala does not support cancellation. Twitter supports cooperative cancellation. Java does provide some cancellation capability. Java Scala interop. The Scala one, you can implement it. The Twitter one provides both types in its API. It tries to provide a Java-friendly API. And Java, obviously Java interop with Java classes is really good, but there's some type inference stuff that goes on. You have to put more type hints in there than you're used to. So what do we recommend? I mean, the biggest thing that we always say is use whatever your libraries use. If you're in a finagle stack, it's really painful to convert to Scala futures everywhere, just so that you can deal with Scala futures in a bunch of other places. If you're in a finagle stack, maybe try to stay Twitter all the way through, and vice versa. If you're in a Scala stack, maybe it's not worth trying to use the Scala or the Twitter futures unless you need to. So stick with Scala unless you need cancellation or you need the monitoring or you want to use locals. If you need to mix Scala and Twitter, definitely use bijection. It's very solid and easy to work with. If you need to interop with Java, prefer completable future, stay away from Guava. It's just too painful to use from Scala without buying you a whole lot. And by all means, watch this space. There have been several good talks this week about Scala 8.io, a bunch of just kind of general buzz around Cat's effect over the last couple of days. And all these things are moving. So take a look at other talks and pay attention to what's going on in the space. Really quickly, a few things that you can look at if you want models of asynchronous other than futures. Reactive streams, streams, actors, and coroutines are all different things you can do. That's me. I hit my time precisely. If you have any questions, you can come catch me later. Thanks.